Now, we've already talked about mechanical power, so now let's jump into electrical power since we're in our electricity and magnetism unit. Reminder, power is the amount of energy expended per second. It's how quickly you are spending energy is the definition of power, and its unit is the watt, of course. Now, the mechanical power equation was work divided by time, or another way, because work and energy, tomato, tomato, right? Change in energy divided by time. And we're going to come back and we're going to end up using those equations in this lesson. But the equation for electrical power, because we're moving electrons, right? And we can then use that power, or we can then use that energy stored through the moving electrons. We can then use that to do other things, so that there must be some electrical power. The equation is current times voltage. Power equals current times voltage. Now, sometimes you'll see the power equation getting connected to Ohm's law, V equals IR, because voltage, current. So if you know something about, let's say, resistance and voltage, but not the current, you could use Ohm's law to solve for the current. Then you know voltage and current to come over here and solve for power. But that's not something that we are, at least not right now, concerned about. So we're not planning on using that currently. Other places that you have seen power with electrical things, if you flip over any of your cell phone charging bricks, you'll end up seeing a little thing on it telling you what the power rating is. 10 watts is average, maybe for an iPad charger. You'll see 10 watts and 12 watts. On electric motors, you'll actually see what power rating it can accept and what it can put out there. So you'll see a power rating on stickers for electric motors, really small ones inside toys, all the way up to very large ones. So let's try a few example problems. Let's start out first with just kind of a plug-chug guy. An iPad charger, it comes with an iPad mini, is rated at 5.1 volts, just pulling it directly off of this, and 2.1 amps. Once again, pulling it directly off an iPad mini charger here. Calculate the electrical power output. We can already see on the charger itself what we expect. P equals IV. Let's make ourselves a variable bank. I equals 2.1 amps. V equals 5.1 volts. That'll let me substitute in. I'm solving for P. P equals question mark. So power equals 2.1 times 5.1. which gives me a power rating of 10.7 watts. With significant figures, that would become 11 watts. And you might say to yourself, but hold on, it says 10 watts over here. Well, this is under ideal circumstances. This isn't accounting for the inefficiencies found in the charger itself. Now, there definitely are cases, kind of like with the iPhone charger, the iPad charger, where the electrical power is just doing something electrical, charging another battery. But many, many times, what we're using the electrical power, what we're trying to do with it, is to actually perform some sort of mechanical work, make something move. The principle that you need to realize there is that our idea of conservation of energy still holds. What that means is the amount of electrical power I put in, if we assume 100% efficiency, equals the amount of mechanical power that we end up getting out. So let's take a look at this example problem. I have a Nissan Leaf, little electric car, all electric car. It's battery pack, and I made sure to try to pull actual numbers here. 300 is approximately 360 volts, and it can deliver somewhere around a maximum, if you completely floor it, ideal circumstances, somewhere around 220 amps of current to the motor. Now, if the car, and I did a little background calculations, 473,000 joules of work, that's about the amount of work that's going to be needed to get this 1,500 kilogram car up to a speed of 25 meters per second. So the question is, how long will it take? So if we make ourselves a variable bank, I know I, 220 amps right here. I know V, 360 volts. 60 volts. I'm looking for time, T equals question mark, how long, and I know the amount of work that we're going to do. Work equals 4,073,000 joules. Now remember, energy is conserved. That means electrical power, we'll maybe label it P sub E, equals mechanical power. And I know equations for these. Electrical power is current times voltage, where mechanical power is work divided by time. We could have used change in energy divided by time, but I chose to use work divided by time because I was told the amount of work. Now we can just simply fill everything in and do our calculation. Now this would be a good spot to remind you of the algebra. Notice that the t here is in the denominator. The variable that I want is in the denominator. I've got to get it out of the denominator. So let's multiply the t over to the other side. That way it cancels out over here, leaving me 79,200t equals my 473,000. Now it becomes obvious what my next step is. I have my time on this side of the equation. Let's divide both sides by 79,200. I turn out with 5.97 seconds, or with sig figs, this is going to round up. Looks like I have up here 2 sig figs, 3 sig figs, 2 sig figs. Notice the lack of decimal on these guys here. That's why only 2, the trailing 0, doesn't count. So this is going to end up rounding up to 6.0 seconds, which is a very normal, that's a reasonable answer there. I can kind of take that to probably be true. 6.0 seconds, about 6 seconds to get up to somewhere around 55 miles per hour approximately. All right, another type of problem using conservation of energy, we're going to set the electrical power equal to the mechanical power here, just this time in the y-axis. I have a crane lifting 500 kilogram steel beams. It's trying to lift it up 25 meters in 20 seconds. Now, I made this crane a hybrid, meaning that it has both an electric motor and a gasoline motor. The gasoline motor generally powers an electric motor in a hybrid vehicle. But an engineer is coming along and trying to make sure that the crane doesn't break down if the gasoline motor fails, because gasoline motors have a higher failure rate than electric motors. And so they want to install a battery pack into the crane so it can continue to operate even if the gasoline motor fails. And he knows that the electric motor part can accept a 25.5 amps worth of current coming in. So let's make a variable bank. It looks like we're going to calculate the voltage that the battery pack should have. So we know we're calculating the voltage. We know the current that the crane can take, 25.5 amps. We also know some stuff on the mechanical side. We know the height that we need to raise the beams, 25.0 meters. Excuse me, it's just 25 meters. Also, we know the time that we are going to try to do it in, 20.0 seconds. We also know the mass of the beam here. It's 500 kilograms. Now, since energy is conserved, the electrical power that I put in all can be transformed into mechanical. We're going to assume 100% efficiency. Now, I know the equation for electrical power, IV, and I also know the equation for mechanical power. It's work divided by time, or change in energy divided by time. This time I'm going to use change in energy. If you chose to go at it through the work divided by time method, it would work out to be the exact same thing. But what I realize here is that we are actually increasing the beam's gravitational potential energy. So I'm going to use change in energy divided by time here, and I'm going to change my energy into mg delta h. Gravitational potential energy divided by time. Just to go ahead and point out that it would have worked out to be the exact same thing if we had looked at it through the eyes of work. Let me just kind of quickly sketch down the exact same idea, power, IV for electrical, and what if we did work divided by time? Well, work, this time we don't know the work over here. Instead, we know some things like height and time, right, and mass. So instead, we would end up needing to break work down into the equation force times displacement divided by time. And then one of the principles that we learned was the minimal amount of force needed to lift an object up vertically is equal to the force of gravity. So I'll write Fg for force of gravity divided by time. And I do know the equation for Fg, mg, right? And what you'll notice is it's actually the exact same thing because the displacement that we move is a change in height. So notice how these two are exactly the same. Now I can go ahead and substitute in all the variables that I know. I know the current, 25.5. I'm solving for the voltage, so I'll leave that as V. I know the mass, 500. I know the acceleration of gravity, 9.81. I know the change in height. We're going to go up 25 meters divided by the time in 20 seconds. Now it's simple to just start working the algebra. It looks like the last step that I'd need to do here is divide both sides by 25.5 to get the voltage by itself, which gives me a final voltage that the battery pack would end up needing of 240 volts. All right, so you notice three types of problems. We had one type of problem where it was just plug chug through, power equals current times voltage, but then the vast majority of our problems, we were trying to connect the electrical power equation to the mechanical energy equation, or to mechanical power. Do a variable bank whenever you're reading problems. The variable bank will guide you as to what you should probably do. So make sure to do that. We'll go over all this again in class. We'll talk through, maybe do some other example problems, and then get into practicing it.